For this video, we'll look at vision and image processing. Cameras are very cheap, so they're a very good way of getting a lot of data very conveniently. So you take a picture, capture an image, and then you've got all the data within that image. The problem is there's a lot of data there to process, so trying to extract the information you want is the difficult part. So a very quick overview how cameras work. You have a piece of silicon that is doped, N-type and P-type doping, and when you've got a series of electrodes on this, you can create some potential wells. So the purpose of these potential wells is when a photon comes onto the material, it creates an electron, and this electron is held in position at that part of the material because of this potential well. So you keep this, you do this collection for a certain length of time, and then when you finish capturing the image, what you do is then you set appropriate voltages on these electrodes, which then shift all these electrons along, and you can download or you can read the value of how many electrons you are as they get downloaded to the end of this array. So that's the basic principle of CCD cameras. I want you to bear in mind that the view we see is not necessarily the view a robot has to see. So we look ahead, but in principle, a robot can have any field of view. So here's an example of an omnidirectional camera. So it's essentially a normal camera looking at a highly polished sphere, so you get a full 360-degree view of the environment. Now the way our eyes work is we've got two, and we use that to judge distance. So it's what I usually do in the class is get people to close one eye and try and judge distance with one eye, only one eye open. You find it very difficult, so it's something you might want to try. So we have two eyes, and we essentially are using this principle where if we look at an object here, because our perspective of that object is slightly different from each eye, then we are trained to do this calculation where we know the slightly different perspective, we know our distance between our eyes, and therefore we automatically work out the distance to the object. Okay, so we don't actually use this formula in our heads, we just train to do this over years of practice. But if you break it down mathematically, then if you have two cameras separated a certain distance apart, and if you both recognize the same object in the field of view, then by measuring the angular displacement of that and knowing the distance between the cameras, it can work out the range of that object. So that's a very good way of just using a camera to actually judge the distance or measure a distance. The slight problem with that is you have to be able to recognize the object in both cameras. So it's that object recognition and matching the features. That's the difficult part. A slight advance on that principle comes with 3D cameras. So this started off with the Kinect a few years ago now. These are now not really getting made, but the technology is still out there. So these are the latest versions of such technology, the RealSense cameras. And they use a very similar principle to this. However, I just clear that screen. However, rather than using two cameras to look at the image, what they do is they have an emitter here, and they send out beams of sort of spots of light onto the object, and then this camera then views these different spots of object, these different points of illumination. So it's the same principle as stereo vision, except rather than two cameras, one camera is now an emitter, and then the other camera picks up where these points are. And then by using triangulation, it can work out the distance. So this would be a typical, in infrared, this is the array of spots of light being sent out by the sensor, and then the camera measures where these spots of light are and does that calculation, and from that you can get a measurement of how far away each object is, or each pixel is within that scene. It's called structured light, and although not as accurate as a LiDAR, you are capturing the whole image in one go. So them sensors are starting to find more and more use in robotics now, in order to sort of measure distance. Okay, so if we go back to our just a normal picture, so just a normal image, not a 3D picture, just a normal image. What we'd like to do is convert that image, so rather than having lots of information there, just try and extract the pixels of interest within that image. So what we're doing is converting a full image into what's called a binary image. And the binary image is just your image consisting of either a value of 0 or a value of 1, where 0 is a pixel we're not interested in and 1 is a pixel of interest. So we can convert between them in various ways. If it's a black and white image, we can just use the intensity of the light of the pixel and set a threshold. So above a certain intensity, we'll class it as a pixel of interest. If it's a color image, we can use color segmentation. So for example, we might want to look for a green object in the environment. So we'd pick out any pixels that are green colored. But ultimately what we're doing is we're taking an image and converting it to just being either essentially black or white, a binary image. Once we have that binary image, so here's 3 examples. We've taken an image, we've sort of converted it, so we've getting rid of any pixels we're not interested in, and we've ended off with these pixels of interest, which are colored dark in this case. Given that, we now need to determine how many objects there are in that image. So you can see in this case, it looks like there's one image, there's one object. In this object, in this image, there's 2 objects. In this image, you could argue is the 4 objects, so we might have 4 objects next to each other, or we might have 1 object. Now we can use our perception to try and work it out. In terms of a computer, you have to have some kind of algorithm in order to process this. And this is where connectivity comes in. And what we can do is define a rule to say a pixel is connected to another pixel by considering how we define that connectivity. So we can say either 4 connected, so pixels are regarded as being next to each other or the same object if they are connected either vertically or horizontally. Or we can go for an 8 connected scheme by saying if any pixel within the proximity of that pixel is sort of highlighted. So if we go back to this example, discard, rerun. Then if we go for 4 connected, so for 4 connected, these are all connected together. You can see they're all connected horizontally or vertically. So we've got 1 object here. These are connected and these are connected. So we've got 2 objects, and these aren't connected to anything. There's nothing above or below these. So we've got 4 objects in this example. If we change that and go for an 8 connected scheme, so if we say 8 connected, then 8 connected is any pixel in the proximity. So in this case, they're all connected together. So we've got 1 image or 1 object. Here, that is actually connected via that. So here we've got 1 object, and here they're all connected that way. So we've got 1 object. So depending on what rules you have for connecting objects or pixels together, defines how many objects you've got in the field of view. Once you've got your object defined, so for example, here we've got this object defined, you then need to recognize that or give it some characteristic features to make it useful. There's various ways to do that. We can compare it to a template. So if we go back to this case, just clean it up again. Our template might look something like that. So our template looks something like that. So if we see this, it looks, okay, that kind of matches. So that is identified as one object. So we could use template matching to identify objects. The slight problem with template matching is the magnification. So we're assuming everything is at the same size. If the camera is slightly further away or slightly closer, then that image is going to or that object is going to change in apparent size. And also orientation. So if that is orientated the other way, will our matching take account of that? A potentially easier way of doing it is looking at maybe enclosing it in a specific shape. So for example, a bounding rectangle and perimeter. So again, if we go back to that case, rather than trying to match this object here with this template, what we could do is just draw a rectangle around that and then measure the perimeter of that rectangle and say, okay, that our object is defined by this perimeter size. So it's a slightly easier way, and then orientation doesn't matter in this case. So we can recognize features in various different ways. So there's lots of approaches. Just for quickness in this module, what we'll do is a very simple approach, and what we'll look at is area and center of the object. So the area is fairly simple to work out. Just count up the number of pixels there are, and then in terms of center of area, you're adding up all the x values and finding the average, and adding up all the y values and finding the average. So again, if we go back to this example, we've got an area of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we've got an area of 10. And then we could add up all the x positions. So if this is 1, 2, 3, 4, 5, 6, 7, 8, we've got a 2 plus a 3 plus a 3 plus a 3 plus a 4 plus a 4 plus a 5 plus 5 plus 5 plus 6. Add that all together, divide by 10, and that's your average x. Similarly with y, and we'll find the center is probably somewhere around there of the object. So we can do some simple to complex processing of the image in order to try and recognize features and where they are on the screen. Now typically an image will be a color image. So when you take a picture, it's usually 24-bit, and that 24-bit represents a red, green and blue component. So your red is represented by 8 bits. So you've got 0 to 255 in the color range of red, similarly in green and similarly in blue. And you can plot these out on a cube essentially. So you've got a red value, a green value, so your red value, a green value and a blue value. And depending on how many components you've got in each of these, then that will plot out. So if you've got quite a lot of red and a lot of blue and not much green, you're probably going to be around here somewhere. So you're going to have kind of like a purpley colour. So where colour segmentation comes in is when you have an environment that has got a lot of artificial colour and you use that to help the robot work out where it is and what it's doing. So it's a false scenario, so it's not really applicable to real world applications, but it's good in terms of sort of specific robot competitions, for example. So this is a RoboCup. So this is developing robots to play football. And they use colour segmentation to help the robots sort of do this job. So they've got a green pitch. You can see green pitch, bright blue goals. a bright orange ball. So you use a bright orange golf ball as the football. And you can use colour segmentation to identify where the ball is in the image and then get the robot to go to that. So as an example, if we take this image here, so for example, say there's another robot and it's taken this image of the scene and it wants to try and identify where the football is and go to it. Well, the first thing we need to do is convert that image into a binary image. So we're looking for the ball, so we'll try and have a look for anything that's orange coloured. So we'll take our colour image and we'll pick out any pixel that's got a red value between that range and any blue and green values between that range. And then any pixels that meet that criteria we'll highlight as we need. So we'll highlight with a 1, otherwise it's a 0. So by running this rule on this image, what we get is this image out. And you can see there's bits of orange here, but this is your main orange. So what we could do at this point is use our connectivity algorithm and connect up. So this is then defined as one object. We've got an object here, got an object here, etc. Lots of objects. We'll then we'll work out the area, and this area comes out to be the largest, so we'll keep this as our area of interest. And then given we've now identified that and as our object of interest, we'll work out the center of area. So we've worked out the area to identify this is the object we want. We'll now work out the center of area of that object. So if we sum up all the x values and average them, and sum up all the y values and average them, we'd get to a point around here somewhere. And therefore, from that colour image, from our original image there, the robot knows it needs to head into this direction here in order to interact with the football. Now you can see we're trying to pick an orange ball out, and the ball is actually here, but because of the light intensity, it's actually quite bright on this part. So it's a white colour, which means our thresholding hasn't quite worked. So it's worked for most of the orange, but not quite all of it because of this bright part on the top of the ball. So what we can do is, rather than use our RGB values, we can use normalized RGB, and this is essentially it's the fraction of that component compared to the total intensity of that pixel. So it's a fairly simple calculation. So our normalized values is the red value is just the red component over all of the components summed together. Similarly for green and similarly for blue. And if we do that calculation and then replot our binary image, you see it actually is picking up the orange a lot better and eliminating some more of the noise. So if you go back to, that was just using normal RGB, using just our standard RGB. If we use normalized RGB, the image improves. And again, we can do a similar, find the center of area, and then get the robot to go to that position. We've been discussing RGB as the colour scheme. There is another colour scheme called HSL, hue, saturation and luminance, sometimes called HSI, which is hue, saturation and intensity. It's the same thing. But where we had our colour cube there with our red, green and blue components, HSL is slightly different in so much as it's this shape, where you have an intensity in this direction, a hue, which is essentially the colour going around in a circle in this direction, and then the saturation or the quality of the colour going radially outwards. So it'll be grey within the centre, and then in this case it's going to very sharp bright green here. So our RGB can be converted to this HSL representation with just, so this is approximately what the formulas are. I don't need you to memorize this, this just gives you an idea of what it is. But you can convert your RGB values to HSL values using the appropriate formula. And then that gives you sort of advantage in sometimes extracting some of the colors you want. The downside is this calculation does take time. So it takes usually a long time to process one single image. So if you're doing extra calculations on top of that, it even takes longer time to process. So the disadvantage is the time it takes, but the advantage is, I can show you in this example, we've got a picture of a barn, and say we've got a robot out there wanting to sort of locate where the barn is and head to it. If you look at your RGB image here, it's going to be quite difficult to pick red, green and blue thresholds to actually identify where the barn is in that image. If on the other hand you convert it to HSL, then what you can do is then use the H component to look for a very bright orange feature in that image and head to that. So sometimes HSL has got the advantages that you can extract sort of certain colors from an image, downside being the processing time required. Now we've been talking about colors of images, so although that works, the problem in a real environment is you don't necessarily know what color something is. So for example, if you tell a robot to go to a certain car, then you need to identify, you need to tell it in advance what color that car is going to be. So although color segmentation is good for very sort of man-made, structured, prepared environments, in the real world it's not ideal. So what we're going to finish with in this video is looking at sort of trying to detect features just from an image without doing any sort of false modification to the environment. So it's just a raw image, and how do we extract data from that? And what we're going to do is pass a filter over the image to extract sort of the edges of different objects within the image. And we'll be looking at two filters. We'll be looking at the Sobel filter and the Laplace filter. So what we have is an image. So if you imagine looking at, for example, a wall with a window in, the wall part will be this, and then when you get to the window, the image will get bright because the sun's shining in. Okay, so that's our, if you imagine that is our view of a wall with a window in. The wall part's dark, and then when you get to the window, it gets bright, the image. What the Sobel does is looks at the gradient of this intensity. So if you run a Sobel filter over it, where the gradient gets steep, it maximizes. So what the Sobel filter will do, it won't tell you where the window or the wall is, but it'll tell you where the edges of the window compare to the wall. The Laplace is the derivative of the Sobel, or the second derivative of the intensity. So if you look at the derivative of the Sobel, it goes positive, and then 0, and then a negative gradient, and then flat again. So the Laplace compared to the Sobel, it's a steep gradient, and then at the peak of the Sobel, it's actually 0 on the Laplace, and then goes negative and down. So the edge of the window in the intensity image is a change in intensity. In the Sobel filter, it's the maximum of the Sobel filter. In the Laplace, it's the 0 crossing point. So these filters have identified where the edges are of our objects. In order to apply these filters, it's just essentially running one matrix over another matrix, multiplying them out and adding them up. So to give you an idea of where these matrices come from, if you imagine you have got an array of data, so this is your image with different values in, and this is value y1, y2, y3. I think I've used y. Yeah. And what we can see is this would be a certain value. corresponding to the intensity at that pixel. The gradient of that is, so if we take this point here, the gradient at that point is the difference in intensity. So we can say y3 minus y1. So that is the change in intensity from there to there over the distance, over 2. So the gradient at y2 is this value here, which is y3 over 2 minus y1 over 2. And if this is y1, and that is y2, and that is y3, essentially we're taking minus a half of that value, none of that, and plus a half of that value. Okay, so the gradient at that point is minus a half of that value, plus a half of that value. So this is what we have here. So we extend that a little bit, and rather than just take the values at either side, we take the values above and below as well. It just adds a bit of smoothing to the function, gets rid of a bit of noise. But essentially you have that ratio if you're subtracting from this side and adding on this side to get your value in there. This is the x direction. You can do it in the y direction similarly. And you can find a magnitude of that if you want by essentially a magnitude and direction by just taking the values of here and doing the calculation. The Laplace is the second derivative, or the gradient of the gradient. So again, we can have a quick look at that. So if we just get rid of that. So we'll say y1, y2, y3. So the difference between these two, so the gradient between these two, so the gradient at that point here is y2 minus y1, and that's a distance of 1 between these, so that's over 1. The gradient at this point is the difference between these two, so that is y3 minus y2 over 1. So that's the gradient, and we want the gradient of the gradient. So we want the gradient between there and there. So that is that minus that over the distance of 1. So it's y3 minus y2 over 1 minus y2 minus y1 over 1. So that equals y1 minus 2y2 plus y3. So if we draw that, and that's our y1, y2, and y3. We've got one of them, we've got minus 2 of them, and we've got one of them. So if we go back to our presentation, so the gradient of the gradient corresponds to that. Again, if we do it in two directions, we've got 1 minus 2, 1 in that direction, similar to that. So for full 2D, you get this shape. So that's our Laplace filter. We can have another filter. This is called the Gaussian. And what this does is, because we're differentiating, this tends to amplify the noise in the signal. So differentiation always increases noise. So we can use the smoothing function. And if we run this filter over, what you're essentially doing is just kind of doing a weighted average of the pixels around to just try and get rid of some of the noise. So as an example, if we look at that, if we have an intensity data here, so this is our original image in terms of intensity, we can use some thresholding. And we can say, well, we want to extract our object because our object is anything brighter than a pixel value of 10. And if we do that, then that defines our object here. The alternative is we can use one of our filters. So we'll try running a filter over this. So if we just go on to I'll need both windows open at once for this. So I just shrink this slightly. So what we can see is to run our Laplace filter. If you look at, so we've got a grid. So we've got 1, 2, 2, 1, 1, 2, 2, 1, etc. 2, 1, 12, 11, 2, 3, 11, 11. So our Laplace filter was a 1, 1, minus 4, 1, 1 scenario. So that was our Laplace. So if we look at this square here, if we look at this one, that is going to be 2 times by 1, a 1 times by 1, a 1 times by 1, a 2 times by 1, and minus 2 times by minus 4. So that is 2 plus 1 is 3, plus 1 is 4, plus 2 is 6, minus 8 is minus 2. So this should be a value of minus 2 if we run a Laplace, which is, as you can see, is minus 2 in this location here. If we do it again, if we do it on the next square down, do it in green, this square here is going to be a 2 times by 1, a 2 times by 1, a 3 times by 1, a 12 times by 1, and a 1 times by minus 4. So that is 2, 4, 7, 19, minus 4 is 15. So this value will be a 15, which again you can see over here. So that's how we work it out. We take each pixel, multiply up with our corresponding what filter we want to run, add the values together, and then that's our value in our sort of our masked file. So when we run this, we get these values, so minus 2, 15, etc. And when on the Laplace, we said the edge of an object is a change in sign, so it goes from a 0 crossing. So this was our object we identified by thresholding. When we run the Laplace filter, you can see the 0 crossing where the edge of our object is. You do get some noise in the data, so you will get sort of some occasional noise, but the edges of objects should clearly show up with the 0 crossing. You'll also notice that we haven't actually filled out values around the outside of the image, and that's because we cannot calculate values because they go beyond what the image is. The way around that is what's called zero padding, and what you do is you add zeros to your original image all the way around, and if you do that, you can then calculate values in these corresponding squares. Okay, so that's what zero padding is known as, and there's an example of that in the exercises. So here's an example, going back to our image of our football and our robot. So we did color segmentation, try and define orange, so we found it that way. However, if we don't know what colors are, and we wish to use filters to try and define where the edges of the object are, then these are our Sobel filters. So this is a Sobel X, Y, and a total one. And you can see the Sobel filter, it's highlighting where the edges of objects are. And then alternatively, this is our Laplace. And you see it's highlighted. It's not necessarily highlighted where the goal is, but there's a very clear definition of lines there of where the edges of our robot, etc. So it's extracting features from an image not necessarily knowing what the image is going to be, but it's highlighting where the edges of objects are. And from that, you would do subsequent processing to try and sort of work out, for example, what is the shape of that object, etc., bounding rectangle. Okay, so I would just like to finish this video with a very quick mention on neural networks. So what we've discussed here is sort of dedicated algorithms for specific processing of an image. The way the technology's moved forward now is most of image recognition and image processing is done through neural networks, sort of deep learning. What a neural network is essentially a mapping function where you have a set of inputs and then these interact. So you combine these through a set of additions, etc., multiplications, feed through different layers, and what you get out at the output is some kind of output recognizing what the input was going to be. Now, the strength of neural networks is you don't have to do all these calculations, what's in here, all these connections. What you do is you set this up, give it some data to start with, and tell it what the output should be for that data. The neural network trains itself, so it recognizes that, and then hopefully when you employ new data, so in this example, a picture of a different cat, it should recognize that as being a cat because it's been trained to recognize the difference between animals. We have discussed processing algorithms, so simple ones for robotics, but how technology is moving forward, it is sort of the neural networks is now becoming the main way that robots are using images from cameras to recognize their environment. Okay, so that finishes this video, and in the next video we'll look at sensors used for measuring force.